Okay, so today we will conclude the proof of the Erdos-Kac theorem. We are nearly done, and I will explain the only remaining principle that needs to be understood. Now, so far, what were the key ideas? So, you have an abstract random variable, sequence of random variables x sub p, where p runs over the primes, which takes the value one with probability 1 over p and 0 with probability 1 minus 1 over p. We are assuming that our x sub p's, they are mutually independent. Now, in this scenario, what can you say about the expected value of x sub p minus 1 over p? Okay. So, x sub p minus 1 over p takes the value 1 minus 1 over p with probability 1 over p. So, this is equal to 1 over p into 1 minus 1 over p plus with probability 1 minus p, x p minus 1 over p takes the value minus 1 over p into 1 minus 1 over p. Okay, this is 0, of course. In general, if you had x p minus 1 by p raised to the alpha, okay, so what is the expected value of this variable raised to the power alpha? So, it takes the value 1 minus 1 over p raised to the alpha with probability 1 over p, and it takes the value minus 1 over p raised to the alpha with probability 1 minus 1 over p. Okay. And so, this is an observation that we make and remember, and you have got f sub, what you did was you defined f sub p on the set of natural numbers, say up to n. Okay. It takes either the value 0 or 1 depending on whether, sorry, not 0 and 1, it takes the value minus 1 over p or 1 minus 1 over p. Okay, where, so f sub p of n is equal to 1, sorry, it is, yeah, 1 minus 1 over p if p divides n, and it is just minus 1 over p if p does not divide n. Okay. And it will turn out that if you raise f sub p of n raised to the alpha, okay, let us say your n is the greatest integer of some positive real number x. If you raise f sub p of n raised to the alpha and take 1 over x times the summation of alpha power of f sub p to the n, alpha is some positive integer, say, okay, then it will turn out to be what it will, because of the way that we have defined it, it will turn out to be actually equal to expected value of x sub p minus 1 over p raised to the alpha plus an error term, let us say it is O of some g of x, where your g of x is little o of 1 as x goes to infinity. Okay, so, this is the crucial idea. This is an abstract random variable on which your central limit theorem can be applied, and f sub p of n is the explicit arithmetic random variable on this restricted space of natural numbers that we have, and it does, as x goes to infinity, this appears to converge weakly, it appears to converge to the expected value of this alpha power of x p minus 1 over p, and this can be made explicit in terms of an error term which goes to 0 as x goes to infinity. This is the key idea, and because of this, once we have knowledge about this side, we can adapt it to knowledge about this side. And as last class was dedicated to just understanding how this side can be related to the moments of omega of n that we are looking at, and today we try to understand how these two are related. And this is not just true for these powers of f sub p of n. We could also take suitable products of f sub p of n raised to the alpha, where p varies over different primes, and similar types of results hold. So, this is what we are going to understand today. Okay. So, as I mentioned last time, the key theorem that we have to prove today is the following. So, we have to prove that. So, let y is some non-negative real number, it grows, we will also impose the condition that this goes to infinity as x goes to infinity. Last time we took a very specific example of this y which appears to work for the problem that we have. So, in general what you have is that if you take 1 over x and then summation of over n less than or equal to x, and then take the sum of all primes up to y f sub p of n raised to the k, k is some natural number, okay. This turns out to be equal to your expected value of summation p less than or equal to y x p minus 1 over p raised to the k plus O of pi of y raised to the k over x. Okay. Actually, this, the way we are stating this equation will work for any y, but of course, our goal would be to choose y in such a way that pi of y raised to the k should be little o of x. So, asymptotically this and this will match. So, this is what we have to prove today. So, let us start with the proof. Now, before we prove this theorem, I want to just state an elementary lemma, let us call this lemma B, which states the following. If you take the sum of all natural numbers up to x such that n and a are coprime, okay. Let us say you have a to be, a is some fixed number which is less than or equal to x, but you choose a and you fix it. In terms of this a, so you are trying to sum up all those natural numbers up to x which are coprime to a, and this turns out to be equal to x times phi of a over a, where phi denotes the Euler phi function, plus an error term of course, which is actually at most to the order of the number of divisors of a. Okay. So, the proof is very simple. So, what you are counting when you want to count all those natural numbers up to x which are coprime to a. So, by invoking properties of the Mobius function, this just means that you are running over you have an inner sum running over sums of mu of d, where d divides GCD of n and a, and you know that the inner sum contributes the value 1 if and only if your GCD of n comma a is equal to 1, otherwise this is just 0. These are your elementary property of Mobius function that we have seen before. So, now with this we interchange summations. So, what we do is we take, so d divides n and it divides a, n is less than or equal to x. So, let us run over all those d's which are less than or equal to x and which divide a and bring mu of d out. And what are you left with in the inner sum? You are left with all those multiples of d which are less than or equal to x, right. And we know this to be equal to x over d plus O of 1, right. So, this turns out to be equal to x times, you are running over the sum of mu of d over d, where d runs over all the numbers up to x which divide a, right, but a is less than or equal to x. So, we can write this sum simply as it is running over all the divisors of a, okay. And then you are left with an error term which is of course at most the number of divisors of a. So, O of d of a. And we have also studied the formula that this sum just turns out to be exactly equal to phi of a over a. All right. So, this is an elementary lemma which we are going to use in our calculations. As I mentioned before, we are following the proof of Erdos-Kac's theorem by Granville and Soundararajan, which was further simplified by Zivrodnik. And so, the simplification by Zivrodnik was to relate these FPs to the abstract variables x sub p and apply CLT to x sub p. The way Granville and Soundararajan continue with this approach is they do not compare it to an abstract random variable as such, they just do very explicit arithmetic calculations with respect to this. So, that modification I will put in your take home exam. But meanwhile, let us just complete the proof of theorem A as we wrote it. So, our goal, as we see on the right hand side, is to study the following sum. So, we have 1 over x summation n up to x, and then we have summation of p less than or equal to y f sub p of n raised to the k. Okay, this is our goal. Now, let us simplify this. So, this is 1 over x summation n less than or equal to x. So, if you take the kth power of this sum, expand it as a sum what does each term in that expansion look like? Okay, so this will look like the sum over all k tuples of primes up to y, and I am putting, instead of just writing them as P1, P2 and so on, I am writing them as P1 dash, P2 dash, in order to indicate that there could be repetitions as well. So, I am taking all possible k tuples of primes coming from primes which are bounded above by y, and then you have f P1 of n, f P2 of n, all the way till f sub p sub k of n. Okay. What do we do with this? At this point, so this is a very nice idea of Granville and Soundararajan to, so far we were looking at average values of fp of n's. What they do is they combine the different, they combine this function for different primes in a very nice way. So, here is a notation that we are going to use. So, suppose you have a number m which has the unique prime factorization, let us say p1 raised to the alpha 1, by the way these are all primes, yeah, p2 raised to the alpha 2 up till let us say pr raised to the alpha r, where each alpha I is at least 1 and all the pi's are distinct primes. Okay. Then we define the number, we define the square free part, not really the square free part as such. What we are doing is we are taking basically all the primes that show up in the unique factorization and take their product, call it capital M. After p sub r, okay, and define your f sub little m of n, where n runs over any natural number. So far we learnt what is the definition of f sub p of n. How do we expand that into a definition f sub m of n? This will come from the unique factorization of m, and this will turn out to be equal to, let us define it as, okay, first I take f sub p sub j of n, raise it to the alpha j, and do this for each prime that shows up in the unique factorization. And remember, this power alpha j is coming explicitly from the prime factorization of m, okay, which is the subscript. It does not change with n. Okay. M is fixed, it is n that is changing, and you are trying to understand the average value of f sub m of n as n runs up to say some x. In terms of this notation, let us call this whole thing star. What does it become? Okay. So, what in terms of the notation in which we are writing this, okay. So, this is basically 1 over x summation n up to x, okay, of sum over all the k tuples of primes where repetitions are allowed in the tuples. And what do you have? F of p1 prime, p2 prime, all the way till p sub k prime of n. You are allowed to write it in this way because of the way you have defined your notation. Okay. And now we interchange the sums. So, let the outer sum run over all the tuples, k tuples of primes up to y, and then in the inner sum you have 1 over x summation n up to x of f p1 prime, p2 prime all the way till p sub k prime of n. So, it is this average order that we have to evaluate, right. Okay. So, this is how we relate this expression that we want to evaluate to these functions f sub m of n. Here our m would be equal to p1 prime, p2 prime up till p sub k prime, the product where there could be repetitions. So, what next with this? So, let me state another proposition. This proposition states the following. So, as before, let us have m, let us have some fixed positive integer m with unique prime factorization of the form p sub r raised to the alpha r, and let capital M be equal to the product of the distinct primes that show up in this in the factorization of little m. Then 1 by x summation over n up to x of f sub m of n turns out to be equal to the following term. This is the main term, j goes from 1 to r, okay, of 1 over p sub j times 1 minus 1 over p sub j raised to the alpha sub j plus minus 1 over p sub j raised to the alpha sub j times 1 minus 1 over p sub j. This is the main term. Okay. As I mentioned at the beginning of this class, each of these is related to the expected value of the variable x p minus 1 over p raised to the alpha, right, and this is just the product of those. But this is not an exact equality. There is also an error term which depends on the this r, which is the number of distinct prime dividing m. So, in terms of that, this is your error term. Okay. Now, typically r would be something fixed and your x is something that goes to infinity, and so the error term would go to 0, or sometimes, as in the original proof of Granville and Soundarajan, your r is taken to be something that varies along with x. Okay. So, with the help of that you can do a direct calculation, but more about that later. Let us just follow through on this proposition. So, how would you solve this? So, let us prove this. Okay. So, your capital M is the product of the PIs, and if your GCD, here is our first observation, if the GCD of n and m is some d, this d is obviously square free since capital M is square free. It is a combination of a product, it is a product of a combination of some primes lying among the prime factors of capital M. So, if the GCD of n and m is equal to d, then our claim is that, and this is very easy to check, your f sub m of n turns out to be exactly equal to f sub m of d. Okay. Which is because a prime will divide n if and only if the prime divides d, because of the fact that your GCD of n and capital M is equal to d. Okay. So, reason being that p sub j divides n if and only if p sub j divides d. Okay. So, we are taking some arbitrary natural number n, okay, and reducing it to a number d, the value of f sub m at a number d, where d is some square free number whose prime factors lie explicitly among the prime factors of m. Okay. So, what this means is that if you have to evaluate the sum f sub m of n, what you can do is you can first run over all possible divisors d of m, and then in the inner sum consider all those n up to x whose GCD with m is exactly equal to d. So, n less than or equal to x and then you have f sub m of n in the inner sum, but we just saw that that is actually equal to. So, what we are basically doing is we are breaking down. So, you have the set of numbers up to x, you are putting it in different, you are partitioning it on the basis of what is its GCD with capital M. Okay. So, now this inner term f sub m of d does not depend on n at all, just depends on d and m. So, you can actually bring that out. So, you have summation d over all the divisors of capital M, then you put f sub m of d, and then in the inner sum you are left with all those n up to x whose GCD with capital M is equal to d. This is a sum which we understand well. So, another elementary fact from number theory, which I think you can easily check yourself, is that you keep the inner sum as it is. You see, if GCD of n and capital M is d, what that means is GCD of n over d and capital M over d is 1, and we also see that n over d will have to be less than or equal to x over d. So, to say that what we are saying is that since we are counting the number of n's for which this happens, my claim is that there is a 1-to-1 correspondence between the set of all n's whose GCD with capital M is d and the set of all n primes whose GCD with capital M over d is equal to 1. I will let you verify this yourself as an exercise. So, in the inner sum what you have is summation over all, let us say n prime less than or equal to x over d, such that n prime and capital M over d is equal to 1, and by lemma B we understand the inner sum. So, what is this equal to? D dividing sum over all the divisors of M, f sub m of d times by our lemma B. What does this turn out to be equal to? It is equal to phi of m over d over m over d, okay, times x over d plus the total number of divisors of m over d. In order to not confuse d and d, I will write the divisor function now as tau. Okay, so this cancels off. So, what is your main term? Your main term is just x taken out, and you have summation sum over all divisors of capital M n, of course, all positive divisors. So, you have 1 over capital M f sub m of d times phi of m over d. So, you see there is a nice analogy between the two terms. If the prime factors that show up in D are exactly those which do not show up in capital M over D. Okay. So, I take capital M out, and then you have summation. You have learnt that both the function f sub m of d and phi, the Euler phi function, can be expanded in terms of the prime factors of those respective integers. So, what you have is, so your m was just your p1, p2 up till p sub r, okay. And then you are running over all those divisors of this p1, p2 up till p sub r, okay. And what is f sub m of d? It is the product of over j going from 1 to r, okay, of f sub pj of d raised to the alpha sub j, okay. And you also have phi of m over d. So, first you have, this is your term corresponding to f sub m of d, and then you have, for what do you have, product of over all those j's, so that your p sub j divides capital M of d, okay. And what do you have? It is just those p j minus 1, right. And then now we can take these inside the corresponding product. Some of them will go here, some of them will go here. We also recall what is this function. It is equal to, the value differs whether your, based on whether your p sub j divides d or not. So, what you now do is x over, so yeah, okay, let me write this again, x over p1 up till p sub r, okay. Now, what you take is d dividing p1 p2 up till p sub r, okay, product over j going from 1 to r, okay, which is, and what are the terms in this product? It is 1 minus 1 over p sub j raised to the alpha sub j if p sub j divides d, and it is just minus 1 over p sub j raised to the alpha j if p sub j does not divide d. But we know that p sub j does not divide d if and only if it divides capital M over d, right. So, you have this, and then you have the other product, over all the prime divisors of capital M which do not show up in the prime factorization of d of p j minus 1. So, now basically what we can do is, we can take, so when we say that d runs over all possible divisors of p1, p2 up till p sub r, what we are taking is basically a collection of sub collection of primes lying among the primes p1, p2 up till p sub r. Okay. From this product here, okay, those primes which do not divide D, whatever their value is, I shift those values to the next product. Okay. And so, in the first product I only stay with those primes which do divide D, and then you have got all the primes outside, take them inside, take some of them in the first product and the others in the next product. Okay. So, what is going on is this is equal to x times, you end up writing this as summation over take all possible subsets of 1, 2 up till r. Okay. Then you go in the first product, go over all those j which lie in S, okay, and you are left with one corresponding to each such j. You have 1 over p sub j coming from here times 1 minus 1 over p sub j raised to the alpha j, okay, times the product over all those j's which do not lie in S, in other words they lie in the complement of S. So, corresponding to those again you have 1 over pi's, okay, divided. So, you have pj minus 1 divided by those pj's. So, you have 1 minus 1 over p sub j times this term coming from those primes which do not divide D. Okay. So, minus 1 over p sub j raised to the alpha j. This is your main term. Okay. And what is this? Okay, if you see, this is a nice combinatorial identity which is exactly equal to the product over all the j going from 1 to r, okay, times what are the sums, what are the terms, 1 over p sub j into 1 minus 1 over p sub j raised to the alpha j, okay, plus 1 minus 1 over p sub j times minus 1 over p sub j raised to the alpha j. Okay. All I am saying is, suppose you have a product over j going from 1 to r of the terms aj plus bj, and you expand this, okay, as a sum. So, in that sum, every term in that sum will have some collection of aj's and the bj's will come from what remains after taking away those corresponding j, which is what is captured in this sum that we see on the top. You are running over some subsets of 1, 2 up till r, then you are taking the collection of j's lying in that set S times a product over j lying in the complement of that set S. Okay. So, that is like taking aj1, aj2 up till a sub jk times bi1, bi2 up till b sub I sub l, which will come from the indices that remain, right. And therefore, this sum here is exactly equal to this product over here, and right at the beginning of the class we saw that this is related to the expected value of x pj minus 1 over pj. So, we are now ready to conclude the proof of theorem A with this. Oh, of course, we also have to look at the error term. This is giving us the main term. What happens to the error term, right? So, what was our error term? Remember, your error term was of the form. So, error term was summation. So, error term summation over divisors of capital M f sub m of d times O of tau of capital M over d, right. So, when you take the O out, so to speak, you have to just make the observation that absolute of f sub m of d, the way we have defined it, is always bounded above by 1. Okay. So, this is just O of summation running over all the divisors of m, tau of m over d. Now, obviously, tau of m over d is bounded above by tau of m, and then you again have, you can take tau of m out, and then you are again running over the sum of all divisors, running over all, the sum runs over all the divisors of m. So, this is just O of tau of m square. Okay. So, this gives you your proposition. So, what was your proposition? Combining this together. Okay. So, now we are ready to prove our proposition C. Notice here your tau of m. So, m was just P1, P2 up till P sub r, right. So, tau of m here, what is the total number of divisors? Okay. It is just 2 raised to the r. So, tau of m square is 2 raised to the 2r. Okay. And therefore, combining all of this together, okay. So, what we have is summation. So, we have 1 over x summation n up to x, okay, of summation, the inner sum is running over primes up to y, f sub p of n, okay, but this whole thing raised to the k, where k is some natural number. What we saw at the very outset, that this is equal to, okay, sum over all possible k tuples of primes, where each of the primes is a prime less than or equal to y, and then you have f sub p1, p2 up till p sub k prime of n. Okay. We interchange summation, and so far from what we have done, we know how to evaluate each of the inner sums. So, this is equal to summation p1 prime running over all the k tuples, where each pi prime is bounded above by y, and you have 1 over x summation n up to x of this. So, what does this turn out by the proposition that we just wrote? This turns out to be equal to x times our product. So, what we are doing is, so let me write this product first. So, j going from 1 to r, and this 1 over p sub j into 1 minus p sub j raised to the alpha j plus -1 over p sub j raised to the alpha j into 1 minus 1 over p sub j. Okay. Plus, so you actually is not closing here, x times this plus O of 2 raised to the 2r, okay, where now what is this r here? Basically remember there were repetitions among the pi primes. So, you are basically writing them as p1 raised to the alpha 1, p2 raised to the alpha 2 up till some p sub r raised to the alpha r, where these pi's are now distinct. Okay. So, now what happens to your main term? So, of course, all of this is 1 over x times this thing. So, x cancels away with x. So, you are just left with something very explicit. So, now you are running over, the outer sum is running over all possible k tuples of primes up to y, and again by basic combinatorics, okay, this sum and this product basically can be combined together as follows. It will turn out to be. So, remember this inner thing, what was, so you have summation over p1 prime p sub k prime, okay, where each pi is less than or equal to y, and the inner sum, what is it equal to? As we saw right at the beginning of this class, this is just your product over j going from 1 to r, where r is the number of distinct primes in each such tuple, okay, of expected value of x p j minus 1 over p sub j raised to the alpha j, okay, plus what do you have for error term? You have O of 2 raised to the 2r. Now, r is the number of distinct primes among these k tuples. So, r is certainly bounded above by k, okay, over x times how many terms can possibly be there in this sum. Okay. So, this is the number of possibilities is just pi of y raised to the k. Okay. So, you have pi of y raised to the k, and this sum again will turn out to be just the expected value of the sums raised to the k, okay, plus O of 2 raised to the 2k pi of y raised to the k, which is y over log y raised to the k over x. This is the proposition that we wanted to prove, which relates these f sub p's to these abstract random variables, Bernoulli random variables x sub p. Okay. And last time we saw that we can evaluate the moments of these sums with the help of the central limit theorem. These are just the moments of the Gaussian distribution, plus you are left with an error term, and you have an error term here. Further, when you go back to omega of n minus log x, that can again be written in terms of the Gaussian moments plus some more suitable error terms along with this, and we just have to make sure that our choice of y is small enough so that the error term is little o of the order of the main term. So, all that calculation we did carefully in our previous lecture, and today we just proved the remaining component, that is relating our functions f sub p to these abstract random variables x sub p. As I mentioned, you do not even need to do that, you can work directly with f sub p and derive the Gaussian random the moments of the Gaussian distribution, but that is something which you will enjoy doing on your own, and those of you who are taking this course for credit will work this out in your final exam, take home exam. Okay. So, I will stop the lecture for today.